Swayam Prabha. Digital India. Educated India.
Welcome to the 12th lecture in mechanics of materials. The last lecture we saw what equilibrium equations were. We gave a formal derivation for the force equilibrium and moment equilibrium. We saw that divergence of sigma plus rho b equal to rho a corresponds to the force equilibrium, and moment equilibrium will yield that sigma is a symmetric tensor. The stress is a symmetric tensor in the absence of body couples or body moments. We also saw how to find the arc length of a curve. We saw in particular that the arc length of a curve can be found using this expression, which is nothing but the magnitude of dou x by dou psi vector integrated from psi 0 to psi n. Okay. We also saw what a deformation gradient is. We saw that deformation gradient maps tangent lines in the reference configuration to tangent lines in the current configuration for a curve. It is a linear mapping, and that linear mapping is called as the deformation gradient. In particular, we saw that dou x by dou psi is related to dou capital X by dou psi through the deformation gradient, where capital X is the coordinates of the metal particle in the reference configuration and small x is the coordinates of the metal particle in the current configuration. Okay. Or it is the position vector of the particles in the reference configuration and it is the position vector of the particles in the current configuration. Okay. We also saw what a displacement gradient is. We saw that there is a difference between deformation gradient and displacement gradient. In particular, we saw that displacement gradient is the displacement vector derivative of the displacement vector with respect to capital X. Okay. And then we went about to find what is the stretch ratio of a straight line deforming into an arc length, a curve. Okay. We found that the stretch ratio is given by square root of c times a dot with a d psi integrated over d psi and divided by square root of a dot with a integrated over d psi. If you remember, we define stretch ratio as the length of the arc in the current configuration divided by length of the arc in the reference configuration. Okay. Here A was d psi by dx, dx by d psi, here A was dx by d psi and C was F transpose F and is called as a right Cauchy-Green deformation tensor. This is where we stopped in the last class. Let us go further and see how we can simplify this. Okay. So, we add lambda of A as integral psi 0 to psi n square root of c times a dot with a d psi divided by square root of a dot with a integrated from psi 0 to psi n d psi. Okay. What we add was we add a body in the reference, the same body in the current might have been like this. Okay. With respect to a given coordinate system E x, E y, E z. Okay. I have this body in the current, in the reference configuration you have this straight line wanted along the direction A. Okay. And we saw that this deforms into a curve between those 2 points, those are the displacement of those 2 points, it deforms like a curve like this. Okay. Now, instead of it deforming like a curve, if I say it deforms like a straight line, say this was also a straight line with orientation A, this also deforms as a straight line with the orientation A, then what can I say about F? What can we infer about deformation gradient if straight lines deform into straight lines. So, what is a mapping that will take a straight line to a straight line? A mapping of this sort, x equal to f11 x plus f12 y plus f13 z plus c1, y equal to f21 x plus f22 y plus f23 z plus c2, z equal to f31 x plus f32 y plus f33 z plus c3. These equations I can write succinctly as x is equal to f times capital X plus c, the vector c, right. So, that is the matrix vector multiplication that goes in here, and this f is a constant matrix. Okay. Now, this is the general mapping which will take a straight line to a straight line. Okay. So, what we infer is from here the deformation gradient f, which is dou x by dou capital X, would be this matrix f. This is a constant matrix or tensor if straight lines deform as straight lines. Such a deformation is called as homogeneous deformation. Homogeneous deformation is a deformation where straight lines will deform as straight lines. Okay. Such a deformation is called as a homogeneous deformation.